Hi, welcome to this screencast for topic 9.1 on oxidation and reduction. So oxidation and reduction, really we have talked about way back in HP chemistry when we talked about ionic bonds, because ionic bonds are a perfect example of oxidation reduction going on. One atom's losing electrons, another atom is gaining those electrons. So oxidation has long been used to describe reactions where oxygen is added. Many crucial reactions for supporting life require oxidation as a reactant, and it's important to keep in mind when oxidation occurs, reduction must also occur. Oxidation can occur without oxygen, so even though it's got the word oxygen in its name, it doesn't necessarily have to involve oxygen. And scientists now believe that many aspects of aging are due to repeated oxidation reactions in our cells that accumulate and over time cause changes or damage to our cell membranes and to the large molecules like DNA. And it would help explain why degenerative diseases increase with age. So benefits of antioxidants being just what they sound like, they are prevent oxidation from happening. They don't really know why that works or completely understand how it works, but antioxidants definitely are beneficial to you. So when you eat blueberries or other foods that are rich in antioxidants, you're slowing down that aging process. So what is oxidation and what's reduction? Oxidation is the loss of electrons, reduction is the gain of electrons, and the common acronym is OILREG, standing for oxidation is loss, reduction is gain. It's all about the transfer of electrons. And again, think ionic bonds, but it can happen with covalent compounds too, because most covalent compounds have unequal sharing. So transferring electrons results in the flow of electrons, or what we know as electricity. That's all electricity is moving electrons. So reduction reactions can be used to generate electricity. And that's basically how a battery works, and we'll be looking at that later in this section. Reverse reaction is also possible where you can use electricity to drive oxidation reduction reactions. So when you hear about electrolysis, that's what they're talking about, is using electricity to force a redox equation to happen. It's very important in the mining industries, as well as obtaining chlorine and hydrogen gases. So a redox reaction represents both the oxidation and the reduction. So this would look similar to what we talked about before as net ionic equations. So both have to happen. So if you show the whole reaction, it would show both the species being reduced and the one being oxidized. And electrochemistry is the branch of chemistry that specializes in these type of reactions. It's defined as a chemical reaction where there are changes in oxidation numbers. There's also the option to show just the half reaction involving the oxidation or the half reaction involving the reduction. So for example, my example down here shows that you have magnesium plus nitrogen forms magnesium nitride, and we'll get to this later how you figure it out, but you should realize magnesium is neutral as an atom. Nitrogen's neutral as an atom, but as an ionic compound, magnesium has a +3 charge, magnesium has a +2 charge, magnesium has a -3 charge. So magnesium has lost electrons to be in this compound, nitrogen has gained them. So if we show just the half reactions for each, the half reaction for magnesium would be showing the 6 electrons lost, so they're shown as a product on the right-hand side. And the nitrogen would be showing it's gaining 6 electrons, so they'd be shown as a reactant on the left-hand side. So oxidation numbers. Oxidation numbers are kind of goofy because they're really made-up numbers. Now, in the case of metals, family 1 and family 2, those aren't made-up numbers. Family 1, 1A, they always lose 1 electron. Family 2A always loses 2 electrons. But when you get over to the nonmetals and to the transition metals, then it's really more about, well, the transition metals, what's it reacting with? Is it losing 2? Is it losing 3? And with the nonmetals, especially in a covalent compound, it's really about who's got the most control. So they talk about oxidation reduction involving electron density. So it's really about gaining control over electrons or losing control. And the important thing is that you don't equate an oxidation number to a set number of electrons being gaining control or losing control over. It's just a relative number. A bigger positive number means a greater loss of control. A bigger negative number means a greater gain of control. So a value is assigned to each atom, and technically oxidation numbers are written with the charge first and then the value. Well, an ion's charge is written with the number first and then the charge. So two parts in oxidation number. The sign shows you if it's losing or gaining control, and then the value refers to approximately the number of electrons. Now, I say that even though I just said don't think about it as being, exactly the number of electrons, because we can actually have fractions for oxidation numbers. The rules really follow the rules of electrochemistry, or I'm sorry, of electronegativity. Fluorine is the strongest. It should have the greatest control over electrons. As you move away from fluorine, oxygen, chlorine, they're pretty close. They have pretty good control. As you get over toward phosphorus, sulfur, nitrogen, they have less control. Carbon, even less control. So looking at the nonmetals, it's really right to left. And that's kind of the rules you follow. So the atoms in the elemental state have an oxidation number of 0, which makes sense because the overall charge on it is 0. And you can't have one atom being positive and one negative to add up to 0, since they're the same atom. Simple ions have an oxidation number equal to the charge on the ion. In a neutral compound, they have to add up to 0. In an ion, they add up to the charge on that ion. And then some elements have different oxidation numbers depending upon the other elements. And again, it's the nonmetals from 7A, 6A, 5A, 4A as you move from right to left, and they become less electronegative, and then the transition metals. So then it's a matter of knowing what are the priority order for assigning oxidation numbers. So the usual oxidation number for any element, the ones that we used when we wrote ionic compounds, will take place unless there's something with a stronger priority ahead of it. So for example, if you put hydrogen with fluorine, you would expect hydrogen to be +1. You would expect fluorine to be -1. That's exactly what happens. But if you put chlorine with fluorine, chlorine and fluorine both tend to be -1. So now all of a sudden, fluorine is the stronger. It gets to keep the -1. Chlorine's going to have to pick up a positive charge. It's going to lose control of the electrons. It's not actually going to lose the electrons, but it's losing control because it's in a polar bond. Oxygen tends to be -2, but when it bonds with itself, like when it makes H2O2, as in hydrogen peroxide, it's going to be a -1. Hydrogen is generally a +1, like when it's with HF, but if you have hydrogen with a metal, so like if you have NaH3, now the Na is going to be a +1. The hydrogen is going to have to pick up a negative charge. So the rules, I think, are better summarized in the packet I gave you, but that's the approximate rules. So what I do when you determine the oxidation numbers for each element in the following, what I like to do is assign a number to each one, which obviously that's what they're asking you to, but I look at these and say, okay, Hg and Cl4, which of these for sure will get to keep its oxidation number? What's going to be Cl4? I've got 4 of them at a -1 charge for a total -4 charge. And then Hg being a transition metal can have a varying oxidation number. So it's going to have to be a +4 charge for this to be an overall 0. So my charge is going to be -1 and +4. And I'm going to pause here and fill in the rest of my work and then come back to it so you can check your results. So I'd suggest that you pause this, see if you can come up with the oxidation numbers yourself, and then check your answers against mine. So as you look through these, for each of my examples, I listed the element that I assigned an oxidation number to first because that element had priority. And in the case where there were 3 elements, then I listed the 2 that had priority and left the third one that had the lowest priority for last. And in the case of ZnNO3 the reason I know Zn is a +2 is because the NO3 is a polyatomic ion, so that is bonded covalently before the zinc gets involved. So because there's 2 NO3s, I know that zinc donated 2 electrons. So it's got to be the +2 with zinc, meaning that N has to be the one with the variable charge there. So moving on, as I clear this here, again, a positive number indicates loss of control. A negative number indicates gain of control. So an increase shows an increase in oxidation numbers. It becomes more positive. It shows that the element was oxidized or is losing control. And a decrease shows it was being reduced. So decide which species is oxidized and which is reduced. If I look at this first one, the H and the O are both going to be 0 on this side because they're elemental. So with H2O, H is going to be a +1, O is going to be a -2 as its preferred. So if hydrogen goes from 0 to 1, it means it was losing or it's being oxidized, whereas oxygen is gaining or being reduced. Ca, it's a 0 since there's no charge. Sn, so Ca picks up a positive charge. That means Ca is being oxidized. Its charge goes up. Sn is being reduced. And another hint is that the charge is reduced from 2 to 0. That's a hint that it's being reduced. And on my last example, one of these probably is being neither oxidized nor reduced. Usually it's just one species being oxidized, one species being reduced. So I've got a +1 here on my hydrogen, which is going to give me a -3. I can't quite get the minus on there. A -3 for my nitrogen. Put it down here. I've got a 0 on my oxygen. Be careful you don't think it's -2 there. So here I'm going to have a -2 on my oxygen and a +2 on my nitrogen. And over here I'm going to have a +1 on my hydrogen, a -2 on my oxygen. So my hydrogen is actually the spectator here, or not being oxidized or reduced. Nitrogen is going from -3 to +2. That means it's lost electrons or is being oxidized. And to double check that that makes sense, oxygen is going from a 0 to a -2. I have a little trouble here with my signs. To a -2. So it has gained electrons and is being reduced. And then just one last reminder, and this is really stuff we already know, because transition metals have more than one common oxidation state, if you see Roman numerals on the name, copper 1 oxide or copper 2 oxide, that is designating the oxidation number, and you would go ahead and use that. You wouldn't have to deduce it from the formula itself.